welcome to Yesterday, Today, Tomorrow. My name is Mariana Cordier, and I am your host. Our guests today are going to discuss the amazing projects NASA is undertaking and developing technologies to further exploring space. To give us an insight on these projects, I have two great guests. I have Dr. Nicholas Schmer, who is a geologist and also working on the NASA. Now you're going to have to later explain this for me, the SSERVI project. And I have Professor Peter Sutherland, who is with the University of Maryland, and he's a fire protection engineering. So gentlemen, thank you so much for agreeing to be on the show. And I'll start with Dr. Schmer. Tell me a little bit about what we were discussing before about the Artemis project that NASA has.
Yeah, so NASA has basically started a large new program, which is basically an endeavor to send humans back to the surface of the moon, and they've called it Artemis. For those of you who are fans of Greek mythology, Artemis was the sister of Apollo. And so obviously this is a follow-on to the Apollo missions that are nearly 50 years old to the date almost. So the idea is to send humans back to the surface and start that exploration program of putting people out there and learning new things about the moon.
Why is it important for this type of project in going to the moon? I mean, it almost seems like, it's not anything new. Usually the public is thinking about, well, why do we care about the moon?
Well, so the heritage of Apollo is with us today. So all the technology and tools and software and computers even are all things that were developed as some degree part of the Apollo program back in the late 60s and 70s. The moonshot effort, for those folks who were there and alive at the time who got to witness it in person, was this incredible undertaking technologically, even sociologically. We had to put together things that had never been done before. And so the technology and the software, even the computers that we use today, all were basically fostered during that environment. And so there's this incredible return on investment of that program, not just walking on the moon and seeing things on the surface of the moon, but also all of that. And then we also uncovered a huge number of questions we have about our nearest neighbor. Apollo was just sort of touching the surface, so to speak, of the incredible richness of scientific inquiry that can go on at the moon. And there's also places at the moon we just simply haven't been, and new discoveries since then that have told us that these might be some really interesting places to go explore. So we're delving deeply into that, and then also thinking about sort of how do we bring things into the modern era and actually still continue to have this capability. We can't go back to the moon right now with this effort of NASA trying to redevelop that ability to do so.
So has technology advanced enough for us to really look at going to the moon in a different way?
I think so, yeah. We've got all these new types of rockets that have been developed that are now capable of actually delivering large payloads. So that large payloads include people and all the stuff that's required to keep them alive at the surface of the moon. And then also the sort of technology we need to survive there, right? So spacesuits have modernized. People have come up with new ways to move around on the surface. There's new types of instrumentation that we want to send to the surface of the moon, new types of experiments that we want to do. And we have to do this in some really challenging operational environments. NASA has set for itself a fairly lofty goal of visiting one of the lunar poles. So all of the Apollo missions were centered near the lunar equator. So if you look up at the moon, this is the part of the moon that's lit during the day and gets dark at night when the moon is basically facing away from the Earth. But the poles are places where there are permanently shadowed regions. You have these craters that have never seen light for over billions of years. And there's also areas that basically stay permanently lit all the time. And so, considering the Apollo missions were all done during the lunar day where they had ample sunlight to work in, these are places where there's going to be intensely deep shadow, places that are incredibly cold. Basically, most gases condense to ices in these kinds of environments. And it makes all kinds of interesting challenges for equipment and robots to work in those kinds of environments, and especially challenging for humans.
Well, that's a perfect segue to ask Peter. I have always heard fire in space is just about the worst disaster you can have. And you guys are experimenting with that.
That's right. If you're in a manned spacecraft, not much worse than having a fire on board out of control. It's a defend in space, defend in place environment, kind of like a submarine or a prison or a hospital where there's not really an evacuation procedure. So in space, every astronaut's a firefighter and needs to be responsible for their own defensive fire, and there's no evacuation. So I'm really interested in fires in microgravity. Of course, you need the fuel, the fire triangle, the fuel, the heat, and the oxidizer. But gravity affects everything on Earth and affects every flame that we see. And we're just learning now how much it does affect it because we finally can investigate fires in the microgravity of the International Space Station. And it does.
What does that mean when you're talking about investigating what fire looks like in microgravity?
Well, I think a classic example is a candle. On Earth, it's tall and pointy and bright yellow. And if you light a candle in the space station, which they've done many times, it's blue and hemispherical. So it looks like a marble. And we're studying flames that look a lot like that. And we're discovering new things all the time.
Well, and talking to you earlier, the audience doesn't have benefit of this, but you were telling me that you've got 3 combustion experiments or programs that you guys are investigating with NASA. Can you describe those for us?
Sure. The one that just finished is very exciting. It's called Cool Flames. And these flames are so dim, you can barely see them with your eyes, even with the lights off. They usually don't exist in normal gravity, but in microgravity, because the molecules hang around for so long, you can actually create these cool flames. And so we discovered a new kind of cool flames on the space station just a couple of months ago. The graduate students were so excited, they actually made the discovery, and I'm so proud of them. So that's an example where you can't ever see that type of flame with gravity because it just causes buoyancy and the gases move too fast to see these kind of near limit phenomenon.
Is it just as dangerous, the cool flames, as I guess the other flames in space?
They're not as dangerous because if you put your hand in it, it may feel hot, but you probably won't get a blister very quickly. But if they hang around for a long time, they could damage electronics. They produce a lot of formaldehyde, which is toxic, and then they could transition to hot flames and create a bigger problem.
Okay. And what are the other projects?
Okay, and then there's one looking at fire. So astronauts they're allowed to bring a bag with just about anything in it up on the space station, any kind of clothes, hats. They also have a lot of cooking oils that are flammable. There's tons of duct tape and Velcro. And NASA tests all these things on the ground, but the ground tests don't always equate to the microgravity tests. So what we're doing is we're testing them in space, but instead of having all the hundreds of different materials and testing them there, we actually have a way to mimic them with gases. So we just bring a small bottle of ethylene, it's a gas, and we flow it at different rates, and we can determine how flammable things are, like the nylon and the duct tape that they use.
Wow, that's pretty important. It's funny how duct tape is a universal tool. And the third project?
And the third one is looking at soot. So soot is what makes flames yellow, and it's also toxic when you breathe it. It's carbon. It's very harmful when you inhale it. So we need to learn more about soot. And by going into microgravity space, we can have perfectly round flames that are much simpler for our computational models to predict and to understand why the soot is behaving the way it is.
What about smoke? How does smoke behave in microgravity?
Well, in microgravity, smoke will kind of drift in the direction of the ventilation system. So it'll move slowly from the flame to the recirculation duct, and that's where the smoke detectors are. But if a smoke detector goes off and they get a lot of false alarms, they have to kind of use their nose and try to figure out exactly where that smoke came from. It's not as easy as it is in your house where the smoke goes up, and the smoke detector that goes off is usually where the source of the fire is.
That's really interesting. And Dr. Schmier, that must be one of the most terrifying things for when you're developing these new technologies and instrumentation for, these extreme environments.
Yeah, indeed. In fact, Apollo was a program which was defined by a fire, not in space here on Earth, but Apollo 1 suffered a fire on the launch pad that actually killed 3 of the initial Apollo astronauts and almost caused the program to be canceled. So this is a really essential problem for understanding basically how to do space exploration. You're essentially sealed in a tube with highly combustible atmosphere around you, and a lot of materials that you're dealing with probably have some sort of flammable properties. So making sure that you can safely explore and work in this environment with all your technology around you is a big consideration. And this is one of the things that the space station has been a really fantastic platform for studying all kinds of phenomena like this, and basically doing it safely close to home. I mean, safely close to home here in this case being less than 100 kilometers away from the surface. But what we're talking about with Artemis and these longer term missions is going beyond Earth and thinking about how to survive on places that are as inhospitable as the moon, or even further out, thinking about landing on the surface of Mars. And so when something goes wrong in those kinds of environments, you don't have a rescue team coming to save you. You've got to save yourself, especially when you're on Mars. You're 6 months to a year away from Earth. And even there's a few, several minutes of light delay between communications. So things that have already happened on the surface of Mars don't arrive at Earth until several minutes later. So you have to be in charge of taking care of yourself.
So you really need to know your sciences, and the people you're sending into space really need to be, I think, a little bit more versed in more than one area, wouldn't you say?
Yeah, and the astronauts that we send are highly trained individuals, incredibly competent people who are usually knowledgeable about more than just one area. Most of us, we specialize in one particular thing. Either we get really good at being a doctor or a nurse or a secretary or accountant or one of these things. They go to school for one thing. Astronauts have to know a whole bunch of stuff, sort of be the Swiss Army knife of knowledge to basically deploy whatever they need to solve a problem they're working on. And that actually brings me really nicely into sort of the things that are our Solar System Exploration Research Virtual Institutes, which is kind of a mouthful, called
Yeah, is that the abbreviation that I was reading?
Yep, it's called SURVEY.
SURVEY.
And the goal of the SURVEY program within NASA is essentially to study these kinds of problems and think about, how do humans go about doing exploration in the solar system, and coming at it from just about every angle that you can think of. There's right now, currently, there's 12 different SURVEY teams that are spread out all over the country. They typically have multiple institutions working together, hence the name Virtual Institute. We're not all located in one place. We actually collaborate with a lot of different partners. And the projects are varied. Some people are thinking about, how do you actually train astronauts to go do these kinds of things? What kinds of curriculum can we build to teach them all the different things they need to know and have on their Swiss Army knife of knowledge? Also thinking about the deep science problems that we have to address. Some of the things like, how humans survive in space and their interaction with something as simple as like the lunar soil. The regolith on the surface of the moon, the Apollo astronauts encountered this. It's a horrendous substance. It gets into everything. It's very fine and particulate. It's very rough edged and scratchy, and people are trying to understand, for example, how this interacts with human tissue. So, we can think of going into a mine shaft or something like that, you're exposed to things that might turn out to be carcinogens. Maybe some of the surfaces of these bodies might have materials that you don't necessarily want to be breathing or getting into your digestive system, or into your respiratory system, that kind of thing. And so the teams are all thinking about different aspects of these problems. And the survey team that I lead here at the University of Maryland, we're specifically focused on thinking about how do we go about exploring for some of the resources that we might find at the surfaces of these bodies. Space is a big place, mostly empty. There's not a lot of stuff there, but the objects that we do go to have materials that maybe we can make use of. So if you're an astronaut going to the moon and you want to live there for an extended period of time, right now, the technology is such you have to bring everything you need with you. It's kind of like going to Antarctica or one of the polar regions of Earth. If you want to survive in these really hostile environments, you bring your food, you don't necessarily have to bring your water because you can just melt the ice that you're on, but you have to bring the heat sources that you might need, any sources of electricity, any technology you need to survive in those extreme environments. But on the moon, that's a 3 to 4 day trip away, and you have to lift all of this stuff out of Earth's gravity well. So if you can find things in situ where you're actually at, a great example of in Antarctica, you don't necessarily have to bring water with you, because underneath of you, when you're up on the ice cap, is this huge frozen reservoir of ice. So as a scientist working up on the ice sheet of Antarctica, all you have to do is go outside your tent and bring in some ice and then melt it, and you can drink the water. It's pretty much pure water. And so thinking about those kinds of resources that we can
I
find.
don't think there's any water on the moon, is there?
But that's a good point, though. I mean, on the moon, that was the canonical understanding that we had from the Apollo era up until probably around 2000, 2010. People thought the moon was a desert. There's no water there whatsoever. But then we sent all of these spacecraft to go and orbit and basically image and study the surface of the moon in really great detail. And what we discovered is at the poles, there seems to be a certain amount of water that's frozen into some of these permanently shadowed craters.
So Peter can then use that water to put any fires out at the station.
That's right.
Yeah.
Peter,
Well,
what do you think about that?
Water is universal for putting out fires. Nothing's better.
All right. So we could potentially have an outpost on the moon.
that's ultimately the goal of the Artemis program, is to have a sustained human outpost on the surface of the moon. And so some of these day-to-day concerns that we worry about here, you have to start thinking about how do you keep an outpost like that staffed? How do you keep it properly provisioned? And then what are some of the problems that you're going to run into as you start to like live in an environment like the moon? And so this is something where, you know, inevitably there's going to be a fire. How are they going to deal with a fire, right? You know, maybe there will be a moonquake, and then that would be another problem they would have to do. Maybe there's an impact or something. They have to figure out how a hole got punctured into their habitat, how to fill it and protect themselves from losing all their atmosphere. It's a big challenge, and I think this is one of the reasons why NASA is very interested in using the moon, is because it's a big challenge, but it's in a safer location than Mars.
The closer location than
yes,
Mars.
yeah,
Sure.
maybe safer is the wrong word. Closer is absolutely the right word.
Well, and it's interesting that we're looking at, you know, a future, long-term future of space exploration. And, you know, what does that say about planet Earth? Either one of you.
I can jump in. I mean,
Yeah, go ahead.
the biggest problem I think that our society, our civilization faces right now is climate change. This Eden that we're all living in and enjoying. You know, you can walk outside and have a fresh breath of fresh air, and you know there's water readily available, right? But that environment in which we operate, as people have seen over the last decade or so, is changing, and it's causing problems for our civilization, both in the terms of maintaining our infrastructure, making sure that there's places where people can live and there's the allocation of resources that we need. And it's changing the very atmosphere that we breathe to some extent, right?
And we don't really have anywhere else we can go.
Not right now. This is the only lifeboat we got. And the challenge is that, you know, we don't necessarily know how that change is going to move forward in time. We have models that tell us something about what potentially the outcomes would be if we continue to put greenhouse gases into the atmosphere. And so a lot of our understanding of that comes from this planetary science that we do. We can look at Earth as a planet and see how it fits into the spectrum of planets. And if you look at the planets that sit in our solar system, we have one, Earth, which is, you know, capable of supporting life, and has a very habitable environment for humans and other organisms. And then we have this dry, cold desert of Mars, which has a tenuous atmosphere. But early in its history, we've found by studying its surface and looking at images and sending spacecraft, evidence for a planet that maybe was habitable in the past, that may have had water floating around on the surface and creating river streams and atmospheric exchange. But it doesn't anymore. And then we have our other neighbor, Venus, which is a planet that is extremely hot. The surface is, I like to tell my students, it's like standing in an oven at the bottom of the ocean, because it's a very thick atmosphere that's really hot. It's hot enough to melt lead. And this is a place where you've got a runaway greenhouse effect, where the planet is basically kept warm because of the trapped solar radiation that gets stuck in its very thick atmosphere. And so in our solar system, our own solar system, we have these sort of two end members plus the one in between, the sort of the Goldilocks problem of where it's just right for life and organisms to exist. And our understanding of how those planets' environments have evolved through time tells us something about some of the pathways where Earth could go and how Earth's environment came the way it is, and why we're different from those planets. It's kind of an interesting.
I guess I would say that that James Webb telescope is then also super important because it's checking out our neighbors to see how far out, we would have to go to find, a similar planet, right?
Yeah.
Or not.
Well, so all the space telescopes that we've deployed have been crucial for finding basically other planets around other stars and other parts of the galaxy, and the inventory of that grows almost daily. But the number of planets that we've been able to identify, given our current ability to do that are Earth-like in a sort of similar orbit to their star as Earth, and the star is in a similar sort of place in its evolution as Earth. It's minuscule, it's tiny amount, and they're all incredibly far away. It would take lifetimes for anybody to journey there. If we were to be able to do that, the technology to do that existed. So right now,
Peter, let me ask you, so with all of this amazing work and projects for space exploration that's going on and the plans that NASA has, what encouragement or what do you tell your students about future careers or options in these fields?
I find, I used to work at NASA Glenn in Cleveland, and I find that some students have it in their blood. They just love NASA, and they love the space exploration. They love watching launches on TV or in person. And it's great interacting with them and encouraging them and telling them that if they like engineering and science, that they have good opportunities to work in those fields and help with that exploration. And I just wanted to respond. I think that climate change is a big concern. I really worry about that. And we're seeing it also, it ties back to fires, because now the wildland fires are so much more severe. And there's a really important connection there that we don't understand too well. And one thing is by studying these very small flames in the space station, you may say, why should I be afraid of a flame that you can hold in your hands? It ironically is teaching us about these huge fires. So people are looking at the fire tornadoes, the spinning fires in microgravity. By removing the effect of gravity, we can learn about the basic physics of these fires, which can consume large stands of forest very quickly.
Why is it that, I mean, did it always have these kinds of forest fires and we just didn't realize it? Or is this really something that's, been evolving in more recent times?
It's really, there are a lot of things changing. Climate change is important for this. We have long periods of rain in the spring, a lot of growth during the summer, and then in the fall, really strong winds. And at the same time, everybody wants to live at the end of a dirt road in California. I would love to live there in the forest. They call it the wildland urban interface, but then it's hard to defend these places. And for many years, the landowners have said, hey, there's a fire in my backyard, come knock it down. The firefighters knock it down. But instead of removing some of the vegetation through controlled burns or natural fires, all the fires are knocked down. And so the fuel loading is just becoming greater and greater. And it's all these things conspiring together to make these fires worse.
Yeah, it's so concerning. And when you see them and, the fire in Denver that decimated entire neighborhoods. I mean, nobody had seen anything like that before. And entire neighborhoods, you can see the layout of the developers for where the houses were supposed to be. I mean, I don't know about you guys, but I've never seen anything like that before.
Yeah, there were 100-mile-an-hour winds, and that's an area where you wouldn't expect normally a wildland fire. It wasn't really a wildland fire, it was an urban fire. And what they're seeing with a lot of those fires is that the houses that are up to code, they're much more likely to survive the fire. And the ones that aren't maintained or older houses that aren't up to code, they're more likely to be destroyed.
So that reminds me, and asking you really quick, in about a minute and a half, if you can, what impact has your studies done for the materials that NASA is using for making their, instruments, their, habitats, if they create habitats, things like that?
Well, we just got our data, and so we're still analyzing it. And we haven't had a chance to say if, one kind of duct tape may be better than a different type yet, or if one type of cooking oil may be much more hazardous. But we see that coming. We're working toward that, and also working with NASA with their tests to try to start to influence some of those things.
And Nick, I wanted to give you a chance to shout out to future students real quick. Anything you would say to them about, participating in these future projects?
I would say that these people who would join us working on these kinds of problems, you'll get a chance to work on technologies and things that are brand new instruments, new types of materials, that kind of thing. And you're going to be forging the new generation of technologies and research. I mean, whole industries were created under the Apollo program that didn't exist back then. So, the smart young people who come in today and start studying one of these problems in detail might come up with a brilliant idea that launches a new industry entirely. So
that is so exciting. I love it. I'm going to have you guys come back and talk more about it. Unfortunately, we're out of time. I would like to thank my guests for joining me today, the audience for watching the show. You can catch us also on our YouTube channel, Yesterday, Today, Tomorrow Show, and we're also on Facebook. See you next time.